Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're going to talk about RAM, VRAM, unified memory. So let's dive deep into it. So before we dive deeper into it, we must understand what the heck is RAM. RAM, it's in the name, random access memory. Basically, it's a core of any computer system. Let that be very clear. It does not matter whether it's x86, ARM or RISC-V. It will always be there. Heck, it will be there in microcontrollers. So it's one of those things that is always there, be it console, mobile, PC, server, whatever have you. It's always there. And why do we need it so badly? Well, CPU can crunch. But here's the other, storage is not that fast. So we need a buffer, basically your slow storage. You need somewhere to basically a working table. The best analogy is a working table. So you have a library, that's your storage, and then you have a work table where you are actually doing the research. So you will bring out few books and put them on the tables and do research amongst them. That's your RAM. So for this reason, you need something that is super duper fast, super quick to access, basically latency sensitive. And then you have your bulk storage. So whenever CPU is doing some crunching, generally it's never crunching data directly on the hard disks. They are crunching data on the RAM. And whenever a scenario occurs where you're like, oh, we have to do read data from storage, it slows down. So for this reason, we need RAM. RAM has to be good, it has to be fast, it has to be stable. And without it, it will not work. And not to mention, there's one penalty because we are generally utilizing a capacitor to make the bits. They are very volatile, meaning at the moment power cut happens, all the data, it does not matter whether it's 1 gigabyte or 1 terabyte, it just goes kaput. All the data just gets poofed out of there. So it is volatile. So basically think in this way, when the power cut happens, table disappears. So you must want to make sure that your library is stable. So this is the RAM's point. Basically, this puppy is too fast and your storage is too slow, but it's huge. So you need a buffer, working table. So that's the RAM. Now, what are the requirements that makes RAM RAM? Well, primary requirement is uniform access time, meaning it should not give a damn where the data is being read from. For example, if you are reading data of a CD, DVD, Blu-ray or hard disk drive, where the head is, read head is, will define how much what's the output speed. Physical location will directly affect the access time. That's not acceptable for CPU. So for this reason, it has to be uniform access time, meaning it does not give a damn whether the data is in this coil or this donut or that magnetic ring. It does not care. It's like it should get all the data whenever it wants with a fixed interval, meaning if let's say it's a 1 nanosecond, it should be 1 nanosecond. It does not matter whether RAM is full or empty. It's exact 1 nanosecond. So time basically should not affect it. Basically, and this requirement was long ago there also when we had tape. And this is why I'm showing this. This is a computer core from Apollo Guidance. And yes, this is how we magnetic core memory. That's how we used to. This is the topology of it. So that's the first requirement. It must be unified time, meaning it does not matter, oh, you're reading this, it's very quick, or you're reading that far, it's very slow. No, all of them has to be exact time synced. Another aspect, addressability. Not only the times has to be synced, it should not give a damn where you're reading data from. Like this is a modern silicon cut down of it. So it should not give a damn whether the data is being read from here or here. It should not care. So addressability meaning CPU should have the ability to call this exact bit or byte if it needs to. It's like, bro, give me this one. Basically think in this way, in library sense, it's literally asking an exact word, and RAM should be good enough where it's like, I got you. This is the word that you're looking for. Every single word is cataloged. So it has to be a very good addressable technology, so to say. So it has all the hardware location with uniquely addressed and directly accessible. So the access time is not there. So it's like a computer can actually make a lookup table, so to say, where it's like, I got this, I got this, I got this. RAM is that what you call parallelly accessible. So it's like, oh, I need this, oh, I need this. It's not like, okay, wait for read head to go there. No, it's not like a go from this memory cache to another. It's designed in that way where it can be like, I do not care. It's like all of it is in one table. And how do we achieve it? Well, good old school matrix structure. So in this scenario, we call the matrix structure rows, word lines, and word lines and column bit lines. That's how we can go to exact bit if we need to. We are that good with that. And yes, that means if you have 1 terabyte of RAM, you can literally still find every single bit in them. Like you do not have to read the whole page or sequentially load the data. It's like, I got this. That's the whole point. I got this. That's what makes RAM RAM. So these are the topological requirement. We started with sewing the RAM together. I'm not even joking. These were a very hard, finicky job that women were very awesome at that. And again, Apollo would not have flown if women were not good at this. Trust me, let's be very clear. It was miracle that they could even stitch. It requires a magnifying glass to even see how tiny these things are. And that's how our RAM started. Then we come to DRAM, dual data rate RAM. Now this puppy is designed for CPU. Now you have to understand CPU itself. CPU is not one trick pony. CPU is a general computer device, meaning it can do bulk crunching, it can do random crunching, it can do decryption, it can do hulululu, it can do jingalala, it can do everything in between. So fundamentally it's not a one trick pony. So any system memory has to be designed with that in mind, that CPU can ask anything from anywhere. That's why it requires that matrix data structure. So RAM has to handle random and flexible access pattern, so it can match the CPU random request, meaning this thing, whatever you are designing in topology term, it has to be in such a way where it's like, I do not care whether I have to access this chip or this chip. It should not give a damn. It's like, I got this. That's RAM's duty. That's like CPU will ask any random thing. You have to be able to match it. That's the primary requirement. And system must have low latency. Because it requires such a random access, it becomes very latency sensitive, meaning it's not a big chunk of data that is flowing. It's not a pipe. It's more of a random. So it does not require a very large chunk, but does require very small what you call bits, so to say. So random queues must be handleable. Like you cannot like, wait a minute, I'm loading this page file, so I know where this random bit is, where that would, no. You should be able to handle it in one go. And system RAM must have amazingly unified time, so to say. A uniform access time. It does not matter how big that time is, it must be uniform. Meaning, it's like, oh, I'm taking this bit, it is coming in 1 nanosecond. Oh, I'm taking this bit, it's coming in 5 nanosecond. Yeah, computer is gonna go kaput. So it must be synced. Let that be very clear. Whatever the time delay is, it must be synced. It cannot change. Oh, RAM is full, so it's slow. No. Oh, RAM is empty, it's very fast. Nope. Unified, fixed. So it has to be uniform. If it's not uniform, it's a bad deal, so to say. And bus width, ironically, it does not need huge bus width. You may think because like it requires random, it requires giant pipeline. No, it requires lower latency, but does not require giant pipeline. So how fat your pipeline is, it's very, very narrow in comparison, but it does have low latency, meaning it will very fast. So this is DDR RAM's requirement. Now we come to VRAM. Now VRAM is something different. VRAM is designed as a secondary RAM. Because again, it's not designed to feed general purpose computer, it's designed to feed graphics processing unit. So this puppy is designed for crunching. Basically, GPU is like, I'm not dealing with a lot of things. I'm dealing with this one thing only. So it does crunch and it is very predictable. Benefit of that is your latency requirement goes, you do not have to be very latency sensitive. That's the good part. Now, again, I do mean less sensitive, meaning less sensitive from a system RAM. Not like, oh, don't care, put an NVMe asset. No, not that low. But it has to be like, it's a bit more relaxed, so to say. And then we come to it, because again, it's a sequential load, it does have huge data bandwidth required. Meaning, if you say 256-bit RAM bandwidth, system RAM, that's like, damn, that's fight. When you say 256-bit GPU, it's like, oh, that's a low-cost GPU, man. Because again, look into most 4090s, 5090s, most of them reach 512 bits. And you go into basically AI cruncher equipments, those puppies have what we call high bandwidth memory, basically silicon directly piled on the SoC. Those puppies go up to 4 kilobits, basically 4096-bit bandwidth. That's not highway, that's a country. So it's literally huge. So fundamentally, in terms of, again, it's not latency sensitive, but it is fat pipe. It requires data to come in and go like there is no tomorrow. It needs like lot of data. And access pattern is sequential, meaning in gaming scenario, you will load your texture data there, and the GPU will call from the texture data itself. It knows like, I'm gonna call this texture data itself. So there is no randomness. Again, randomness is somewhat there, but compared to CPU, it's like it might as well be static. So from that point of view, the good part, it's static. Penalty, it is giant. It does not take small bits of data. It's like, it's basically like you have a bottle and you have a bottleneck. Poof the bottleneck and make it a bucket. That's what you need for these things. So bandwidth becomes huge, and it has multiple parallel cores. You need to feed those puppy. So it's like, let it come in. Like bandwidth matters here ludicrously more compared to basically latency. So that's why they are two diametrically opposed system. Basically, one system is like make it as snappy as possible. This is like make it as fat as possible. And another penalty of the physical design and geometry is that these things get hot because they are close to something very hot, which is your GPU, which could easily go up to nowadays to up to 400 watts to 600 watts of thermal output, and there is no dedicated cooling on these things, so they are just soldered there. It's like hope that you can get enough hot air to quote unquote cool yourself. So for example, normal RAM chip could be easily rated for safe temperature of 80 degrees. These have to be rated to 105. So they do require to be much hotter and survive. It cannot be like, oh, I can handle it. Technically, your RAM sticks can also handle it. They just won't be happy about it. This have to be hot and happy about it. So it does require certain, what you call tolerance. Same goes with here, because again, this is literally on the same die as the hot furnace. So those things have to be even more temperature resistant, so to say. So VRAM does have a thermal requirement that is like brutal. Now we come to the new kid in the town, that is unified memory. Shared memory pool for both CPU and GPU. Now, here's the deal. You may find it odd that why do we call this a new thing, given the fact that all integrated GPUs inherently have the same thing. Like, it does not matter how old, like heck, my Intel Core 2 Duo I had iGPU. That iGPU was directly calling data from the system RAM. So why that was not classified as unified memory? Well, simply because the controller matrix was dumb, so to say. So it does require complex controller. This is on a silicon level, hardware level thing. So what Apple actually showed was this idea of making a silicon fast enough where it becomes dynamic. Silicon is like able to handle it, meaning it can allocate. So it's like, hey, I have 32 GB. What do you need right now? Oh, my CPU is doing heavy crunching. Okay, let that puppy swell up. Oh, no, my gaming part is CPU does not need a shrink it, change it. That changing was not possible whenever you're talking about iGPUs or APUs. So that's why unified memory is a different beast, so to say. It has complex memory controller, and if it is implemented correctly, you do not notice it, meaning the programmers will not notice it. It will be done on the back end. You do not have to worry about it. And dynamic memory allocation also leads to another thing. You have to understand, if you're directly feeding CPU RAM to GPUs, GPU would starve. It's like, bro, if you have that like GPU core is like, bro, this is too slow. So you needed CPU system RAM to catch up to GPU level, where the gap between GPU and CPU RAM is low enough where it's like, I can deal with this. So for example, in this puppy, the Radeon cores that is in that silicon is like, bro, I can easily handle like, let's say 512-bit bandwidth. It will like, okay, I will function if 256-bit is there. But if you feed it, let's say 64-bit, like a very cut down, is like, bro, no. So to make sure, you needed system RAM to be big enough. That's why this puppy has 256 bus bandwidth. It needs to have that wide, where it can like, okay, GPU can handle it. And CPU, again, CPU wise is a bit easier because again, it's a system RAM that was upgraded, not a VRAM that was upgraded, because again, VRAM is designed for one dedicated task. It is bad in terms of latency compared to system RAM. So high bandwidth, it has to be there so GPU does not starve. And that became possible nowadays. However, let that be very clear, while your system is dynamically doing this, if you really want to flex on this, like really want to utilize every microwatt of power that is going into it, you must optimize for maximum gains. Otherwise, like, you still gain it, it just won't be awesome. So for that awesome Ultra GG, you do need to optimize a bit, software a bit. And it does make sense for some application. Consoles, now here's the consoles are technically in the gray area, because the older consoles, this was dedicated. It was like, okay, the OS will consume this much and you will have this much. The end, go home. Everybody gets the same dev kit, go home, no problem. In modern system, they do have some amount of, but again, they always want to, because again, it's a gaming console first, they make sure the VRAM is has a dedicated, like it will not go below this, and CPU has a little bit of flex, so to say. So consoles are in a gray area. Laptops, again, this AI chip, AMD AI Max chip was a laptop system. They are like, okay, it cannot be fit inside a laptop. Physically, it can fit. It's just thermal envelope is too huge. So they're like, okay, let's put it in desktop. Framework did that. Mac did that. They managed to fit everything. So this is the whole point. It does make sense for laptops and mini PC. But be very mindful. The moment you put big load, you will start to notice that it's not that great. Why? Many people will say this is the future of computation. No, it's not. There is a dedicated reason why we have two different topology. Very good reason for that. So there are certain GPU cores that are utilized in A100s and something like that. If you feed them with 5 to, or even with Apple, does not matter. You feed them with that, they'll like, what do you mean I only have this much bandwidth? They're expecting kilobits of bandwidth. This puppy will be like, yeah, 512, yeah, good. So fundamentally, you have to understand, it's just turbocharged CPU RAM. CPU RAM has become good enough where GPU core can be fed slowly. So it makes sense when overflowing is a bigger issue. Basically, if you are in a scenario like unoptimized video games where it's like, 12 GB is just not enough because again, people forgot to optimize it, it will overflow. That is a worst case scenario. In this, you will not have that overflow even if it crosses 32 gigabyte. So that is one good thing. And once we have that direct NVMe link data pathway, which again, PlayStation 5 does have that, that will also make this job much easier, because right now you literally have data going to CPU RAM, system RAM, and then funneled via PCI lane to VRAM. Ideally, that's a dual data redundant. You should not need to do that. GPU should be able to directly call the NVMe. NVMe is fast enough nowadays, and again, it is on over PCI lane that it can be directly dumped into your VRAM, and it can be done on principle. Again, right now it's more of a software limitation rather than hardware. Hardware is like almost reaching a point where you can do direct memory access. So unified memory, while it is a cool technology, it's not like, one thing for all. It's a good for laptops, good for tablets. I can see awesome use in those scenarios. But PCs, nah. Servers, heck nah. So this was my presentation on basically 3 types of RAM, and this was just a surface level just to get you started. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.